Okay, so we're taking a look today at polynomial models. So in the last lesson, we looked at how you find the derivative of a polynomial function using a series of derivative rules. Today we want to look at how you can use the derivatives of polynomial functions to solve problems, specifically problems involving position, distance, displacement, and velocity. And the overall thing that we want to be able to do as we move through this unit is get a better understanding of what the derivative means. And when you're looking at a problem, what does the function mean? What does the derivative mean? How can you use information from the function and information from the derivative of that function together to solve the particular problem that you are interested in? So you guys have a copy of the question that we're going to be looking at. So let's just take a look at it here. The position of a small object moving along a straight line is given by this function. Okay, s is a function of t is 2t cubed minus 15t squared plus 36t plus 8, where t is in seconds and s is in meters. Okay? So when we're given a function like this, this is called the position function because it gives the position at any point in time. Now the first thing that we're asked here is, what is the object's velocity at 5 seconds and at 2.5 seconds? So if we're given this position function, how can we find the velocity? Well, what is velocity? Velocity is the rate of change of position with respect to time. Let's actually write that down. Velocity is rate of change of position. And if we want the rate of change at a particular point in time, we want the instantaneous velocity, or the instantaneous rate of change. And anytime we're talking about instantaneous rates of change or instantaneous velocities, we are going to be looking at using our derivative. So we want to find the derivative of this function. And that is going to give us a function that will tell us the velocity at any point in time. So we're going to call that our velocity function. So our velocity function is the derivative of our position function, s primed at t. So what is the derivative of this position function? Well, we can use the power rule and our sum and addition rules. We know that we're going to bring down that 3 as a coefficient, multiply it by the 2 to get 6t squared, subtracting 1 from the 3. Then we're going to bring down the 2 in our next term, multiply it by the negative 15 to get negative 30t. And then finally, our 36t just becomes 36. And that 8 just disappears because it's a constant term and its derivative is going to be 0. So now if we want to find the object's velocity at 5 seconds, we just have to sub in t equals 5 to this velocity function. So we're evaluating the velocity at time 5, which is just going to be, well, 6 times 5 squared minus 30 times 5 plus 36. And we work all this out, and we can get 36 meters per second. Now, if we want the velocity at 2.5 seconds, we can do the same thing, subbing in 2.5. V at 2.5 is going to be 6 times 2.5 squared minus 30 times 2.5 plus 36, which, punch this into our calculator, we get negative 1.5 meters per second. So one of our velocities here is positive. The other velocity is negative. What does this tell us about our particle, or the motion of our particle? The direction, yeah. So if this is traveling in, if our velocity is positive, this is moving in the positive direction. Or I'm going to say moving to the right. If our velocity is negative, our particle is moving in the negative direction. So I'm just going to say it's moving to the left. because we usually draw our graphs so that positive is to the right and negative is to the left. So this lets us think a little bit about what the motion of this particle is going to look like. It's going to start off at some point here, time equals 0, and it's going to be moving forward. It's got to come back, and it's got to start moving backwards this way, and then it's going to start moving forward again. Okay? So the two times that we have been looking at here has been, there's 1.5 is somewhere here in the middle, right here in this backward stage, and t equals 5 is down over here where it started moving forward again. Okay? So moving forward, positive velocity, moving backwards, negative velocity. Okay? So if this thing starts off moving forward, then starts moving backwards, then starts moving forward again, what is going on here and here? If it's changing from moving forwards to moving backwards, what does it have to do in between going forwards and going backwards? Right? It's got to stop. So that brings us to our next question. When does the object stop? Okay, well, it's going to stop when it goes from moving forwards to moving backwards, and then we want to find the position at these two times. So how can we figure out when this thing has stopped? Well, what does it mean that it has stopped? What's its velocity at that point? Yeah, so we want to find where the velocity is equal to 0. So we have this function, v at t equals 6t squared minus 30t plus 36, which we said represented our velocity. We want to figure out when this thing is equal to 0. So how can we figure out when that function is equal to 0? What do we need to do? Riley, how do we solve for t? Emily? We got to factor this thing. So first thing, we're always going to look to see if we can common factor. 6 is common here, so let's factor out the 6. T squared minus 5t plus 6 equals 0. Then we're left with a trinomial in the brackets there, so we can factor that trinomial. We'll get t and t, and let's see, 6, we've got to have a 3 and a 2. And then to get a positive 6, they're either both positive or both negative, but if we're going to get a negative 5, they have to both be negative. So we get t minus 2, t minus 3 equals 0. So our two solutions are going to be t equals 2 and t equals 3, are when the particle is stopped. So we got to actually say that. Particle stops at t equals 2, t equals 3. Now it also asks us, what is its position at these times? So what should we do in order to find the position? I mean, plug the t's into the equation. Which equation, though? No, go ahead. We only have two equations, right? We've got v at t and we've got s at t. So which one do we want to sub it into? The original one. Yeah, if we're looking for position, make sure we sub it back into the position function. Okay? So we're going to do s at 2 and s at 3, okay, which are going to work out to be 36 and 35. So always in these questions, you're going to have two functions, or maybe more functions, okay? Position function, velocity function. Make sure when you're subbing things in, you're subbing them into the correct equation or the correct function for the thing that you're looking for. So next up, when is the object moving in the positive direction, the negative direction? Okay, so we've already established that it is moving in the positive direction, or moving to the right, when the velocity is greater than 0. And it's moving in the negative direction, or to the left, when our velocity is less than 0. Okay? So we want to figure out which intervals correspond to velocity being positive, velocity being negative. And the tool that we can use to do this is we can set up an interval table. Now, you did this back in advanced functions. Okay? We know that our velocity is equal to 0 at t equals 2 and t equals 3. So we're going to use those two values to divide up the intervals in our table here. So we're going to have one interval here at t equals 2. We're going to have another interval over here where the break is at t equals 3. And then in between them, we're going to have intervals of time. So we're going to have an interval here from 2 to 3, an interval over here from 3 to, I'm just going to say positive infinity, and then an interval over here from 0 up to 2, where our time starts at 0. And we want to figure out in each of these intervals, is our velocity positive or is it negative? So what we're going to do is take our factored velocity expression and check the sign of each one of those terms. So our velocity function was, we had a term that was 6 that we had factored out. We had t minus 2 that we had factored. And our last factor was t minus 3. So I'm just writing those terms in that column there. And we are going to check to see what is the sign of each of these three terms in each of these three intervals. So I'll do the first one here because it's the hardest one. 6 is always positive. There we go. Now what about the term t equals 2? In the first interval, is it going to be positive or is it going to be negative? And how do you know that it's going to be negative? Exactly. You can imagine picking a number that is somewhere in this interval. A good one to pick is something like 1, and just imagine subbing in there. 1 minus 2 gives you negative 1, so that's going to be 0. So we can keep doing this. We can imagine subbing in 1.5 here. 1.5 minus 2 is going to be negative. And over here, from 3 to infinity, we can imagine subbing in something ridiculous like 100. Okay? 100 minus 2 is clearly going to be positive. And then repeat the process for t minus 3. You're going to point out something I did wrong, right? What did I do wrong? I used 1.5 instead of 2.5. Excellent, thank you. So I should erase that. And when I'm picking a value to use as the test value on my interval, I should actually pick a number that is inside the interval. Okay. So that is going to change this from negative to positive, because 2.5 minus 2 is going to be a positive number. Thank you. All right, let's do the last row here and see. 1 minus 3 would give us a negative. 2.5 minus 3 is going to give us a negative, and then 100 minus that is still going to be positive. All right, and then we want to put all of this stuff together. So to sum it all up, velocity is a function of t. If I've got two negatives and a positive, that's going to give us a positive overall. Two positives and a negative give us a negative overall. Three positives give us a positive overall. So we can sort of sum this up by saying, how should we say this? Positive direction. We've got two intervals. The interval from 0 to 2 and from 3 to positive infinity. And then negative direction. We've got a single interval from 2 to 3. Okay. I've been using these round brackets to indicate the ends of my intervals. The round brackets means that the number at the end of the interval, so in this case the 2 or the 3, is not included in that interval. Okay? So it's everything up to 2, but not including that 2. Why don't I include the 2 in my interval? Yeah, we know that it's not positive velocity at 2, it's not a negative velocity at 2, its velocity is 0, because we found that in the previous question. Okay? So we've got sort of enough here that we can start kind of visualizing what the graph of this position function would look like. Okay? So this is position function as a function of time. We know that if this is time 2 and this is time 3 over here, that what our function has to do is it has to be going in the positive direction, or up, on this graph from 0 to 2. Then it's got to go in the negative direction, or down, from 0 to 3. And then it's got to go back in the positive direction. So I should kind of label this as positive and then negative. Okay. Question? Okay. 2 last questions here. Same function. We want to determine the net displacement over the first 8 seconds. And then the next question is determine the total distance traveled in the first 8 seconds. So really the answers to these questions hinges on what is the difference between displacement and distance traveled. What is the difference between displacement and distance traveled? Shane? Yeah, absolutely. He says it's based on the initial start point to, did you say final end point or something like that? Yeah. Okay. And that's the big difference. Displacement only depends on the beginning and the end. Okay? It doesn't matter what you've done in between, okay, where you've gone. It's just from the beginning to the end. So all we really need here is we need to know the positions of our endpoint and our start point. Well, let's see. Our starting point is t equals 0, so we want to find our position at t equals 0. And our ending point is t equals 8, so we want to find our position at t equals 8. Our position at t equals 0 is pretty easy. That's just 8 meters, because everything else is a 0. And if we sub in 8, we get 360 meters. So our displacement is just going to be the difference in those two. So I'll do 360 minus 8 gives me 352 meters. What about distance? If displacement does not depend on the path traveled, distance is the exact opposite. Depends on the path. And what we mean by that is if we're moving forward, that contributes to our total distance traveled. If we're moving backwards, that also adds to our total distance traveled. Okay? So we have to take into account when our particle is moving forward and when our particle is moving backwards, and to figure out the distance it travels in each of those cases. So I'm going to phrase that as that we have to consider the magnitude or the absolute value of the distance in both directions. So fortunately, in this question, we already know a lot about how our particle is moving. If it starts here at t equals 0, we know that it's moving in this direction up until t equals 2, where it stops. and goes backwards a little bit to t equals 3, where it turns, stops, and turns around again, and then it heads off for the rest of the problem. And we know that t equals 8 is going to be sort of down here. So we can take the motion of this particle and divide it into 3 little sections. This first section where it's going forward, I'll use an I there. The second section where it's coming backwards, and then the third section where it is traveling forwards again. So we want to find the magnitude of the distance traveled, or the total distance traveled, in each of these 3 sections. So to do this, we need the position at each of these times here. So we need the position at time 0, the position at time 2, the position at time 3, and the position at the end, time 8. Now, we've already calculated most of these positions. 8, 36, 35, and 360. Okay. So we want to take these and figure out, in this first interval here, let's see, our first interval is going to be from 0 to 2. What is the total distance traveled? Well, the distance is going to be the absolute value of the end point minus the start point. So the absolute value of 36 minus 8. Okay? And the absolute value is just there to make sure that we treat it as a positive, as contributing to our total distance, even if the answer is negative. So if we do 36 minus 8, we get 28 here, okay, which is positive anyways. In our next interval, we can call this D2. We want to do the same thing. We want the absolute value of our endpoint, 35, minus our starting point, 36. Now in this case, our answer would be negative. 35 minus 6 would give us negative 1, which tells us that it's moving backwards at that stage. But we want, even though it's moving backwards, we want to add that to our total distance. So we're going to take the absolute value and make it positive 1. And then finally, in our third section, our third distance, we're going to take the absolute value of 360 minus 35, which gives us 325 meters. So if we want the total distance, we just add those up. So 28 plus 1 plus 325 is going to give us 354 meters. So our total distance is 354 meters. Our displacement was 352 meters. So these aren't the same. Our distance is larger than our displacement. Now, does that make sense that our distance is larger? Everybody's nodding their head. Who wants to take a shot at explaining why here? Radhika? Yeah. So the path where it's moving backwards doesn't count to our displacement, but it does count to our distance. And in fact, it counts twice. So this part here in section 2 here, where it's going backwards, that 1 meter, we add that 1 meter on as it's going backwards. We add it again when it's going forwards to give us that difference in 2. So your total distance should always be larger than your net displacement.